Flipped classroom video for Maths A2 Unit 3, Constructing Differential Equations. So, if we're going to construct some differential equations, then we probably need to know what a differential equation is. And differential equations are equations that include derivatives in them. Now, you're perfectly used to finding derivatives, so finding dy by dx or d2y by dx squared, but differential equations are a bit different because they already include those derivatives within them. So, for example, we might have d2y by dx squared plus 4dy by dx, take away 6y equals sine x. And they are hard. To solve them means learning a lot of techniques, but fortunately for now we're going to be looking at the simplest ones, and then you will possibly build up through your mathematical or further study later. Okay, we're going to be looking at situations when we know how the rate of change of a quantity, and remember dy by dx tells us how y is changing in relation to x, so that's what we represent rate of change by in a familiar way, dy by dx, or we might have dx by dt if we want to see how x is changing in relation to time, or t. So these situations we're going to look at are where the rate of change of a quantity is related to the quantity itself. For example, you may know already, possibly from Science GCSE or from your general reading, that the amount of radioactive decay, or the rate of radioactive decay, is proportional to the amount of radioactive material we have. Okay, so that means we have the idea of half-life, which means that half of the radioactive atoms will have decayed in a certain time. And if it keeps being a half, then we can see that the amount of decay is related to how much we have, or how many particles we have. So if we write n as the number of radioactive particles, which obviously will be massive, but thankfully we don't have to deal with numbers at the moment, but we write n as the number of radioactive particles, then the change of this over time will be dn by dt. So that's the change of the number of particles over time. And since this is proportional to the number we have, then we can say that dn by dt is proportional to n. And that means that, as you will know from previous study, that the proportional sign we can replace by equals a constant. So it means that dn by dt is equal to a constant times n. And this is called a first order differential equation. We'll have a look at a couple more examples. So real life. When I say real life, it's modelling real life. Or rather, real life is represented by a model, but nonetheless these are sort of roughly like what happens. So for mobile phones, the value of a mobile phone falls in proportion to its current value. Okay, so it might halve in a certain length of time, in a similar way to radioactive decay, in fact. So we can form a differential equation that shows this. We call the value of the phone P. And what we've been told is that dp by dt is proportional to minus p, because it's going down. And that means we can write dp by dt equals minus k times p, and because we know it's going down, we can say k is greater than 0. Another example might be, say, draining a tank. The example actually is not draining a tank, it's a tank that's leaking. But the idea is the same, that we might find from experiment that the amount of water leaking through a hole in the floor of a tank is proportional to the square root of the volume of water. So again, we can form a differential equation that shows this. If we call the volume of water V, what we've been told is that the change of volume, which is what is leaking out, is changing the volume, so dV by dt is proportional to minus the square root of the volume, or the square root of V. And this time we're going to use lambda as our constant of proportionality, so we can write dV by dt is equal to minus lambda square root of V. And again, because we know that the volume is decreasing, with the leak or with the drawing off of the water, then we can say that lambda is greater than naught. Now, we will look at solving these sort of equations in another video, which is M 2.3.7f, called Separable First Order Differential Equations.